And its recording has started now. So your participation gives us permission to use the audio and video if you use that. We do intend to post this onto YouTube or publicly available channels on the EPRI.com website, potentially RTE website. So it will be available afterwards. We will also make the slides available afterwards in some form, either via email or via publicly accessible link. So you should have access to all the materials as and when you need it in the next couple of days. We have opened a poll question with WebEx. So if you click, I believe, on the bottom of your page, there's a three dots for polling. It should appear there. So we've got a couple of questions that we'd like you to answer as we go through. If you'd like to be involved or get some more information from our email circulation list, please put your name and email in question 1. If you have some comments or feedback, pop them in there to us. Note that we won't see them live, so if you want to ask a question live, you have to use the chat. We also have a question 3 is, where should we be focusing our attention in the years ahead with the competition in 2022 and beyond? And then question 4, would you be interested in getting involved in the collaborative? So feel free to tick on those and we'll follow up afterwards. I'd like to invite you to introduce yourself in the chat as well. If you want to put in your name, affiliation, it's always a good way for people to know who's on and who's contributing to the comments and webcasts. If you have questions, pop them in the chat as well. We'll take them in real time. We won't invite people to come off mute, but if you do have questions, we'll get to them as and when we need them. So it's a packed agenda. We've got 90 minutes or so. We're going to open just with an introduction from myself and the project team, talking about L2RPN and the concepts behind it and the ideas behind it and what we want to achieve. I'm going to pass to Anton from RTE. He's going to talk about the 2021 challenge in particular, how that was different from previous challenges, especially with the aspect of trust. We'll move then to the three winners from 2021's competition. So we'll invite on Enlight from Austria, Horacio Martinez from Argentina, and Polixer from China, who will have, there's a video presentation there, so 10 minutes each, and they'll go through their strategies and their thoughts on the challenge. We move then to a discussion by Malta Lena from Fraunhofer, who's going to discuss the AI2Go initiative. So that's taking L2RPN and bringing it into realistic use cases. NVIDIA will join us around about the hour. Pavel Dimitrov, who will talk through a simulator tool, a GUI simulator tool that was developed specifically for L2RPN. Really nice initiative, nice tool, nice product. So he's got a video there and we'll answer questions as needed. And then we've left around 20 minutes to talk about, have an open discussion. We have some ideas from where this is going to go. We have a lot of, shall we say, linked initiatives or projects that are out there that we'll mention and touch on. And yeah, we'll invite some questions in the chat there and take them if time permits. So I'll start. Hopefully everyone's introducing themselves in the chat. I'll invite our project team to come on and just say hello, give a name, affiliation, and what it is you do. One by one, I guess. Not everybody is on here. A couple of people send apologies, but let's do it in order. Anton, and then Benjamin, and then Karim from RTE.
Yeah, so hello everybody. I'm Antoine Marot, so the lead AI scientist at RTE. Yeah, I've been working with Adrian pushing this L2RPN initiative. So yeah, very happy to see all of you there today. I'm not sure Benjamin and Karim are yet connected.
Okay.
Hello.
Come back. Oh, you're there.
Yes. Yeah, we are all at RTE in the same room, so we were not sure that we would be able to connect as fast. So I'm Benjamin, and I have helped Antoine with these initiatives, and I also developed a few tools that have been used for these competitions.
Thanks, Benjamin. Is Karim there?
Hi. Yes, I'm here. Hi, Karim. I'm part of the RTE data science and AI team, same as Antoine and Benjamin. I mainly work on mathematical statistical modeling on various topics around the electricity power network and also around electricity markets and economics.
Thank you. So Joshin Kremer sends his apologies from TU Delft. We'll move to Kyuhao Huang and Ramij Raja Hussain.
Hi everyone. This is Kyuhao Huang from PNL. Early morning here. So I'm a power system engineer at PNL, basically interested in working on applying machine learning, particularly reinforcement learning for power system control and operations. Thank you.
And Ramij, if you're on. No, you're on mute. Is Pratik, I don't think Pratik is on, or Dexter. So Pratik Kulkarni and Dexter Lewis from EPRI were key collaborators here as well. And finally,
hi Adrian, I was mute then, sorry for that.
Oh, there you go, Ramij. Yeah, go ahead.
Hi everyone. This is Ramij. I'm a PhD grad student at Iowa State University. My work is basically on power systems and control, and I have also worked as an intern at PNNL. Thanks.
Thanks. And lastly, Mariana Weimann from VNR Energy. I don't think Mariana is on, but VNR Energy were a supporter and sponsor of the prizes this year. I'd like to spend some time just saying thank you. This is a sort of voluntary effort. It's not funded from central research. We get together, collaborate, spend some time, and our company spend some time. So we want to thank our companies, institutions, and organizations for giving us the time to do that, and also sponsors, supporters, and other collaborators there as well. So what is it we want to do with this project? So we have a vision for the future of operations, which is sort of extending on the timeline for where we're coming from in control centers from the 1950s to 2030 and beyond. So it's an operator viewing real time from a distance via a centralized interface, which is called Hypervision. This is connected to fully automated interoperable software tools in orange here on the left, which have a backup of a manual interaction on the right, which can be where the operator can intervene if automation does not work as expected via the interface. Both of these are connected to a simulator tool with full data range and fully interoperable with the tools, but also for training for the operator as required. So to enable this future vision, and this is a vision a lot of system operators are sort of buying into and honing in on, we need to develop tools like using AI techniques to manage the network and monitor the network in parallel with the system operator. We should first, I've done this many times and we usually always get the same questions, so let's preempt those questions. We're not intending to whip the operator out of a control center and replace it with an Alexa style bot to run the power system. So it's not intended, this isn't the intention of what we're trying to do. It's mostly to think of it in terms of an autopilot system. So something that's guiding the operator decision support. So with decision support, so looking ahead with foresight, with full complete data, and identifying where there are issues with forecasts or with system issues such as congestion or voltage in the future. We see this as being the way forward, a kind of parallel approach, and we'll get to that the 2021 competition through Antoine in a few minutes. The second question we usually get is, how far is this away from going in? We should say it's low in the TRL level right now. We're probably many years from production environments, real-time operations. We're working on small synthetic grids because the problem is extremely complex. We haven't tried to tackle the Eastern Interconnect or the continental European system just yet. So start small, try and develop our methodologies and try to scale beyond. So they're mostly the two questions we get asked, and sort of try to keep focus on that rather than thinking about, is this going to be in? It's a research project with a long duration life cycle. Where have we started, or where are we coming from? So using reinforcement learning in recent years has made huge strides through self-learning, Google using self-learning to learn computer games like Atari up here. The team took a lot of inspiration from this learning to run using reinforcement learning project. Again, I think that was Google a few years ago, where reinforcement learning techniques were used to train an agent to run like a human. This prompted Benjamin and Antoine and the guys to try to gamify the project, the problem of network operations, and that's led on to the learning to run a power network. So it's kind of within that ecosystem, taking inspiration and trying to build on learnings when and where we see them. We're also trying to break down this barrier between, or make links, should I say, rather than break down barriers between the power system community and the AI community. So we realize that coming from the engineering community, we might not have the techniques or the ability to think in different ways about how to solve problems. Likewise, the AI community might not have visibility of use cases for the advanced knowledge that they have. So this is an effort to sort of link engineering with machine learning or data science, and we're doing a pretty good job so far. We've made a lot of good connections between both communities to date. And just a note before the next slide is for Antoine to lead into 2021. So this is how the competition has evolved since 2019. So started on a very small grid, that 14 bus grid that I showed. There were no events. It was a winter month, so that the agent had to train itself to control topology only. Moving to spring of 2020, there was a challenge launched where a part of a larger grid was used. It was a medium-sized grid. There was maintenance activities carried out, so the grid was managed and lines were periodically taken out for maintenance, running over long year cycles. And again, the agents could control topology only. 2020 saw a leap into a bit more complexity. So there was two different tracks. A robustness track where the smaller grid was being attacked by an adversarial agent taking lines out at random, and the agent had to control the grid while lines were being taken out at random. They also could control with redispatching actions as well as topology actions, so they could control generation at different nodes as well as open and closing breakers and switching lines. The second track there was on adaptability. So here there were the full range of that grid was used, that 118 bus grid, except it was different dispatches. So one had a lot of renewables and one had a lot of baseload fossil generation. For 2021, we took a combination of the two tracks. So it was an adversarial track using a medium-sized grid, but there was a high amount of renewable variations in the generation dispatch. So you can see here we're building and scaling and hope to keep going through that in the years ahead. So, I'll pass to Antoine, who's going to describe the 2021 competition and the innovations that were made there.
Yeah, thanks, Adrian, for the nice introduction. So, yeah, I will be talking more about this competition we had last year. So this was again submitted in a conference, so ICAP's International Conference on Automated Planning and Scheduling. So more targeted to AI people, but very welcome to any other kind of people. And this was done thanks to our team. So everyone said already hello just before, but yeah, so thanks a lot. Thanks to the partners, especially in this competition, RTE, EPRI, PNNL, and EL2RPN, who really help designing that. So as Adrian mentioned, our goal is not to replace the operator, but really to design new assistants, smart assistants for our operators, especially to deal with those big challenges ahead or already ongoing, such as the energy transition, to cope with climate change. And so here you can just briefly, it's a brief overview of the desired features for us to design such assistants. So robustness, definitely, we want those agents to have some reliability and to be robust to unexpected events. We want them to be adaptable because the energy mix, for instance, is changing quite rapidly, and so agents will need to adapt. And those two were already kind of explored in the previous competitions, but what we were missing was maybe the trust aspect. Next. And so we designed this new L2RPN with trust competition, which ran for about 3 months last year during summer. And the idea here was, in addition to ask artificial agents to operate a grid under a high penetration of renewable energy, we wanted them to be able to communicate with the operator. So basically design a trustworthy agents that are able to communicate when they're in trouble, especially when they might fail. And to do that, so you can see the score now of the competition was not only about scoring the operation cost of artificial agents, but also scoring the ability to send alarms at the right time. And we had actually a stronger penalty if they were not able to send alarms. They would get this minus 200 point score. So quite an incentive to actually be good at it. And on the picture here, you see the grid with 3 possible areas on which an agent can alert, and as well as the 10 lines that could be attacked randomly by the agent. Next. So in previous competitions, there was not this aspect of asking agents to communicate with some other agents, or basically humans. So it was maybe more framed, you could see that as an autonomously only agent, but not very trustworthy yet. Because as you can see on this line here, which represents the operational performance rate, so basically the number of weekly scenarios an agent can complete, we started with a baseline, which was not too bad. And then across competitions, prior winning solutions have made some progress on this axis, but yet we're still far from a nearly perfect agent. And saying that, it means that such an agent will not be deployed autonomously, neither it will be trusted by operators yet. So we aim rather at developing these assistants that can communicate with operators. And if you click on next. So this competition, we wanted to add this new dimension of asking those artificial agents to predict when they might fail. And doing so, then you don't have to have a perfectly operating agent for it to become trustworthy. As soon as you have a good enough operating agent, and then an agent that can really alarm the operator when the operator might need to pay more attention and maybe to take over, then this artificial agent becomes trustworthy for the operator. So that's really what we wanted. We didn't expect participants to maybe improve the operational performance rate, hopefully not to degrade it, but actually to really move across that new dimension, being able to predict their failure. Next. And so here is the shape of the score function for this alarm score we designed. So on the x-axis, you can see the time before game over. So if you are at 0 on the right, it means you just sent an alarm while you were just failing. So that's not good enough, right? You want to communicate that information to the operator ahead of time so that he has enough time to react. So while you're able to communicate that information ahead of time, let's say 30 minutes ahead of time, or 35, which was the ideal time of alarm here, then in the competition, you will get some points for doing so because it was a relevant alarm for the operator. And as soon as you move further ahead, then it's not selective enough to be meaningful. So really, we had this shape for the score function where the best time of alarm was 35 minutes and the relevant interval of alarm was between 15 minutes and an hour. And then we also model this alarm budget or attention budget. So somehow we model the operator that way, because what we want is our agent not to send alarms every 5 minutes, right? So an operator, a human, has a limited capability in terms of attention, and we want the artificial agent to be able to manage that, to take that into account. So the max attention budget at a given time is 3 alarms. You consume 1 budget when you send an alarm, obviously, and you can recover a bit of budget over time, 1.5 alarm per day. So that really gave some incentive for agents to send alarms in a selective and relevant time range. And this encouraged also agents to still finish scenarios and not fail on purpose, because if they finish a scenario, they will get the maximum number of points for this score as well. Next. And our design was based on the trust framework from the literature. So there's a lot of different kind of approaches for that. But here we leverage this approach from Charles Green, where he defines the trust equation, which is based on those 3 criteria. Credibility, which is basically about asking an agent to explain himself and to be transparent on what he's recommending. So we model that in our competition by requesting time and localization of alarm from the agents. It needs to be reliable, so an agent needs to act consistently for similar situations and also knows the limits of its capabilities. So that's basically just what we explained. And then intimacy, you want to build the relationship between the human and the artificial agent over time, so that you have a good relationship quality, basically. You trust each other because you have the right level of relevant interaction, and you have also as little as possible misunderstanding between one another. And we model that by the attention budget of the operator, really to push the artificial agents just to send alarms when it's most relevant. And then you have 2 approaches to quantify the limits of an agent, an algorithm. Either a passive approach, where every time step you basically send your confidence interval to the human, and then the human has to decide what to do with that. But it requires a lot of supervision and it's hard to evaluate. And we rather took the active approach to just send a signal of low confidence when it's relevant to actively warn the user. This can be framed as a sequential decision-making problem with some budget, can be evaluated, and it's also used already today in, for instance, semi-autonomous driving. Next. And here you see the final leaderboard, so the top 5 participants. So this year we got very good participants from all around the world. So previous competition were overwhelmingly dominated by China, but this year, so first best participant was from China again. The second one was from Argentina, despite his his login name, and third place were from Austria. So that was quite interesting. As you can see, actually, they were close maybe in terms of operational performance for the top 3 at least. But what really made a difference was this alarm or attention cost. So there was definitely an incentive for that in our design, and that was nice to actually see those results. Next. And here you can see a quick table over the failing scenarios. So there were 24 scenarios on which the participants were evaluated. And so they succeeded at about 2/3 of them, but they were still failing on the others. And that's where we can best assess how good they were at sending alarms before game over. And basically the best participants managed to send alarms 5 times out of 8 failures. So that was good. And the second participant was able to send 4 alarms out of 8 failures, so relevant alarms. So that was interesting. And then when you switch, Adrian, next, to analyze maybe a scenario and compare those 2 agents. So here you see this scenario over January, over this week. And on the y-axis, we're measuring how the grid configuration is changing over time because those agents are acting on the grid. So you start from a reference configuration, and then over time, you might change, for instance, 6 substations on the grid. And so one agent is failing maybe in the middle of the scenario. As you can see here, it tries to send an alarm, but actually it was too late for it to be relevant. And it was also running out of alarm budget there. So yeah, it did not get any points for this scenario, for the alarm score, whereas best agent actually almost managed the whole scenario. Too bad he failed just before the end, but actually got some points for the alarm score because he was able to send it in a relevant time and still had some budget for that. And you can also get some statistics to see how good they are at managing this budget of alarms. So the best agent is actually better managing it. On average, he has 2.5 alarms available rather than 2.2 for the second best participant. He only spent 1.5% of the time with an attention budget below 1, whereas 10% of the time for the second best agent. Next. And so here, what we do is we analyze the agents through this Grid2Viz study tool. So you can load the scenarios the agents were operating and give it some analysis. So actually it's supposed to be a video, but it's not a big deal. And you can actually run the analysis yourself at this URL below, so Grid2Viz icaps.herokuapp.com. So if you use this URL, it will load in your web browser just immediately, and you can make the analysis yourself. So it can be very, very nice. And last slide. So here is a full ecosystem of basically modules we have to make that run. So at the core, we have the Grid2Op framework to run agents. And then it has many APIs to get data in, and we have a package to generate data. Then you want that to interact with a physical simulator to compute the power flows, for instance. And here you can have several kinds of simulators, one of your choice, actually. And basically, you also have agents that either you program yourself or you take from existing baselines, or, for instance, the best agent at some competitions. And now we can also, as a human operator, interacting through this Grid2Game GUI. And in the end, you want to analyze the performance of those agents with an a posteriori study using Grid2Viz, and you can also have some benchmarking. And all those items I underlined in yellow we'll discuss today later. So best ICAPS agents, some new baselines we are making available to the community, and also what NVIDIA did to provide some new tools or simulator to the community.
Okay, thanks, Anton. So if there's questions, we won't take them verbally. Just put them into the chat already. We've had some good questions from Wayne and Seth, and Benjamin's answering some. So just pop them in, and we'll answer them there directly. So as Anton mentioned, we've had 3 winners videos today, including there's a separate one from the University of Wuhan in China who came 4th. We can't include it for time reasons, but we'll post it on our YouTube channel or on the web page. So we'll go through them, the videos each individually. First up is Enlight from Austria, and the speaker is Matthias Forfer. So hopefully just play this video and it will work.
Approached power grid topology planning with model-based reinforcement learning. So just a quick intro. At Enlight AI, we are basically 6 people working on reinforcement learning. all of us were at some point a little bit involved in our challenge contribution, but the rest of our time, besides working on projects, we are also, for example, developing framework MazeRL. All right, let's get to the central idea of our submission. So after we started playing around with the grid to op env a little bit and looking at previous submissions, we came up with a few design principles that we tried to impose on ourselves. So the first one was we wanted to find a solution that preserves the original action space without pre-computing, for example, fixed limited sets of action candidates, because yeah, this might potentially introduce some bias or even limit the optimal solution. Then the second one is that we wanted to keep grid-specific or dataset-specific engineering as low as possible. Yeah, this turns out to hand-engineered rules that only apply, for example, to the ICAPS 2021 dataset. And yeah, last but not least, we wanted to make sure to work with a methodology that first of all scales well to larger topologies, is somehow a nice fit or a natural fit to AI-powered control room assistance tools, and especially also supports long-term or scenario planning. Yeah, in terms of compute budget that we had available, this was at max 4 compute nodes, each with 64 cores, and yeah, we were training with a single GPU. Except for the restricted compute budget here for reinforcement learning, the upper design principles really work well or fit really well to the AlphaZero algorithm. And now the central idea of our submission is that we extended the RL algorithm AlphaZero to make it applicable to the topology planning problem in large power grids. So yeah, let's just see which steps are required for developing and training such an agent. So I will start with the model training workflow. This is quite general, so we always have in the center of such an algorithm distributed MCTS sampling, which runs in parallel and produces an asynchronous stream of MCTS sampled grid trajectories. These trajectories are fed into a rolling trajectory buffer. Yeah, and once we have enough transitions sampled here, we can feed these into our policy and value network optimization stage. So we train our policy and value networks, and after every epoch, whenever a new set of weights is available, we write the latest version of these models back to the MCTS sampling stage, and the whole process starts from scratch. So this is now the training workflow. In terms of agent interaction workflow, we also took a small modification. So we have here our agent, we have here our MazeEnv, which basically wraps the grid to op environment and adds a few nice features on top, produces an observation, and then the agent can pick a topology action. For the specific problem, we now intercept this classic agent env interaction loop with the critical state observation and skipping wrapper. So what's going on here is that we observe if the current state of the env is critical. If it's not, we simply run a loop just executing the no-op action. But if we really encounter a critical state that requires an action, we now really query the agent to predict actual topology change action. Yeah, and that's already it. Speaking of the topology change action, so this is probably the most important bit of our approach. So what we did here is we took the Bernoulli distributed multi-binary action space of the grid to op env. which is related to the bus switching problem, and converted it into a sub-step action space that introduces intermediate sub-steps on top of this actual nth step that now allows us to take multiple discrete actions at a time. The intuition for this one is, because it's not really time to present the details here, the intuition is that this is somehow a hierarchical autoregressive action selection. And this doesn't require explicit action space reduction, because due to the hierarchical decomposition of the actions, we can apply extensive masking in the lower layers of this selection process, and yeah, this becomes quite efficient, and we can preserve the original action space here. In terms of reward formulation, nothing fancy was used. It's basically just the exponential decay of the weighted sum of the maximum load on any power line and the number or count of currently offline power lines. All right, now to the heart of the method, the MCTS policy. We also took here a few modifications. In general, let's say we have a critical state encountered, then we can sample our actions and build up the MCTS tree. So the first modification, and this is due to the limited compute budget, is that we developed a heuristic value function and don't learn the value function from scratch. An additional change is also related to compute budget, and this is early stopping of the MCTS search process. So once a critical state is recovered or found, we build up the tree, and as soon as a recovery state is found, we just early stop the MCTS search process here. And yeah, the third point in here is also related to this, because once recovery states are found, we don't select the action up here by visitation count or value, but we bias the action selection towards these recovery states. Okay, so the last bit that is now missing are the features and the networks that we employ. So we started out with quite complex graph convolutional models, but in the end we were using quite simple features and models. So these features comprise, for example, line status, loads, current flow, deltas between substations of these features, and so on and so forth. A bit more interesting, we of course use observation normalization to make sure the models learn efficiently, and we also use observation stacking to also have some dynamics of the env represented in our observation. Yes, and all of this is then processed with a simple late fusion style feed-forward model, first processing the individual features, concatenating them, and then feeding into the policy and value networks. Okay, let's just assume these models are trained and we can get to the deployment stage with quite little compute budget actually. So how can we deploy such an AlphaZero model? So on the lower end of the spectrum, we could simply apply argmax policy. On the other extreme, this is what we would like to do, of course, is full MCTS sampling. With a single core on the submission server, this of course is not possible, which is why we opted for a compromise that still works sufficiently well, and this is a form of beam search that we employ. So how does this look like? So we encounter a critical state, and then we take the most probable action. Maybe this already resolves the critical state. At some stages or situations, it might be also required to take multiple actions to really get out of this critical situation, but it can still be the sequence of most probable actions. However, if this is not the case and the sequence of most probable actions, for example, leads to a diverging power flow, we scale up. We call this survival mode and dynamic computation budget. We basically scale up and just explore different branches in this search tree. And yeah, hopefully a few of these trajectories will really recover from the critical state. And yeah, we can preserve the grid in a stable and running state. As we now already have this kind of methodology, We can also reuse it for raising alarms and getting human attention. So we have these multi-step horizon rollouts, and whenever we encounter a critical state that might lead to diverging power flow or blackout with a high probability, then we inform the human operator about upcoming critical situations by raising an alarm. Yes, and this is pretty much our approach in a nutshell. Thanks a lot for your attention, and yeah, hopefully see you in the next edition of the challenge.
Thanks to Matthias and the team from Enlight. If I think you're online, so there's a question in the chat, so feel free to answer that if you can. And yeah, congratulations, very nice solution, elegant solution there. So next up is moving to Argentina. So this is Horacio Martinez, who came second, and Horacio can't join us today, so he can't answer any questions. But
hello everyone, my name is Horacio, and this is going to be a video describing my solution to the competition Learning to Run a Power Network 2021, in which I took second place. Our goal in this competition is to manage a power grid, and to do so we can take certain actions like to connect or disconnect power lines, to change the topology of the grid, or to change the power output of the generators of the grid. One new feature in the 2021 edition is that now we have the ability to raise an alarm if we suspect that the grid may fail soon. They give us two different scores: the operational score that measures how well we operate the grid itself, and the attention scores that measures how well we predict or not predict a failure of the grid by raising the alarm. This combination of the two scores gives us the final score. That is the one that matters for the leaderboard. The grid layout is the same as 2020 edition's robustness track, and if you want to know more, you can follow the link in the bottom of the page. First thing to note is that raising an alarm doesn't affect the grid state whatsoever, so the evolution of the grid is completely independent from the alarm actions we take or don't take. This is going to mean that the operational score is going to be independent of the attention score. So the first approach we could take is to first create a strategy for operating the grid. Once we have this strategy fixed, we can proceed and create an alarm strategy given our operational strategy. This isn't optimal necessarily in theory, because we could have an action that leads to a lower expected value of the overall score, but a higher expected value of the operational score. And we will always pick the action that leads to a higher operational score, a higher expected value. Okay, so first thing we're going to do then is to create the operational strategy. The first problem we face is that the action space is extremely big. At each time step of the simulation, we have over 60,000 individual grid actions. And I looked at previous finishers of the competitions to see how they approached the problem. And the one I liked the most was the second place finisher of 2020. What he did was to try all possible 60,000 actions in thousands of generated scenarios, and then after trying all these actions, he selected the best performing ones, so the ones that leads to the lowest max row being the maximum load rate of the power lines. In this way, he managed to reduce the action space from 60,000 to only 290. So our operational strategy is going to be very simple. What we're going to do is that at each time step, we're going to check if we can reset the grid topology. So if one line was disconnected by an opponent attack or something else, we're going to try to reconnect it and revert to the original topology. if we can do this and we have a maximum row greater than 1, what we're going to do is to simulate all 208 actions, and we're going to choose the one that leads to the lowest maximum row in the result of these simulations. With this strategy, I got a 54.69 as a final score for the operational portion, which was the second place score. Now we can move on and create our alarm strategy. Some things about the alarm in this competition. First of all, the alarm should be raised n times before the failure of a grid. Also, we have to select a specific zone to target with alarm, and this is going to give us a better score if we select the correct one. Also, we have a certain budget, and if we try to raise an alarm and we don't have enough budget, then we can't do it. This budget increases with each time step up to a certain maximum. Okay, so our plan is going to, first of all, run 10,000 episodes and according to our operational strategy. We're going to store the results of these episodes, so we're going to store the state of the grid in each time step of these episodes. Then we can discard the episodes where we complete the entire episode without a failure, because in this case our alarm score will be the maximum regardless of which actions we pick. Then we can also split 10% of these episodes for validation of our alarm strategy. What this is going to allow us to do is to try out different strategies extremely fast, because the only portion that is slow is the simulation of the grid itself. The alarm we can compute very fast. Okay, so the first approach we can take for the alarm strategy is to say we are going to raise an alarm if the maximum row is greater than a threshold X, and we're going to select the zone that contains the power line with this maximum row. How are we going to select the threshold X? Well, we have all these stored scenarios, so what we're going to do is run the different values of X and simply pick the one that has the maximum overall score across all the stored episodes. We can do a little bit better than this, because we're not taking into account the budget that we have, and it is expected that if we have a greater budget, then we can be more lenient on how we trigger the alarm, and if we have lower budget, we probably want to be more constrained. So we can define different thresholds X depending on how much budget we have, and to select them, we do just as before. We try them. We try out all of them in different scenarios. We can also try to create a neural network to predict the probability of being close to a failure at a particular time step. And once we have this prediction of the failure, we can do just like before and raise the alarm if the probability is greater than a threshold of X. And we select the threshold just like before. The features of this neural network could be the simulation state. That is what I personally use because I was running out of time, but it would probably be better if you generate more complicated features. For example, you can take into account previous time steps and combine them, for example, by looking at the delta of some features with respect to the more recent and later time step, and you can probably generate much more features these ways. the architecture of the neural network was chosen just arbitrarily, but trying a few different ones. I didn't spend much time in this, so this probably can be improved. Okay, so how well did all of this work? Neural network alone, not very well. I got the score close to 0. It's probably some bug along the way, but I was running out of time and I didn't have time to debug it. Naive strategy alone gave me a score close to 28, and neural network combined with naive strategy gave me a score of 31.17. So I'm happy that at least I got to use the neural network combined with the naive strategy, and this was the final score. Final score overall was the combination of the two previous one, that was 47.63, and I got second place with this score. Can we do better than this? Well, obviously, but one thing we can try is to use reinforcement learning, because we have a Markov decision process. We have the state, that is the state of the alarm, that is the budget we have, and the time step since last alarm, and this is affected by how we choose to use to raise or not to raise the arm, and we also have the state of the grid that is not affected by raising or not raising the arm. We have the actions, that is to raise the arm and which tone to raise the arm in, and we also have the reward, that is the alarm score at the end of the episode. We could try to use Q-learning, policy methods, and all the different reinforcement learning algorithms. So maybe for the next edition I can try this. So this was everything. Here are some. Hello everyone.
Okay, that's Réseau, who came second, and first place goes to Polixer Technologies in association with Nanjing University, and speaking on this is Qiaojie Wang.
Okay, hello everyone. This is Qiaojie, and I'm very glad to be here to give this presentation on behalf of our team. And at first, I want to show my respect to my teammates, Wen Taoxie and Xingyuan Zhang, and also our supervisors, Gong Junqing, who is the CTO in our company, Polixer Technologies, and Prof. Yang Yu from Nanjing University, who is also the CEO of our company. And also thanks to the staff and organizers of this competition, because I think it is a very great competition, and these 3 months of competition could be a very amazing and unforgettable experience in my life. So I want to say thank you guys all. The following is the outline of my presentation. At first, I want to show you the pipeline of the method developed by our team, and then I will explain the corresponding technical details of each part in the pipeline of our method. At the third part, I will show you the match results, and at last, I will give a brief discussion about the future works. The first part is the pipeline of the developed AI-based electronic system. For each time step, the system will first take the observed grid state of the power net as input, and the expert module will first try to fix the power net with expert knowledges. And if the expert model cannot fix the overflow situation, the AI-based module will give some suggestions about how to fix the power net. Then, if these suggestions are all useless, it means the system cannot solve these issues of overflow. Our system will give a judgment on the emergency degree of the current overflow situation. And if the emergency degree is very serious, the emergency module will use the predefined emergency actions to save the power net and also raise an alarm with the alarm module. So this is the whole pipeline of our system. The following, I will show you the technical details of each module in our system. In the expert module, the system will first detect if there are any disconnected lines. If yes, the system will first try to reconnect the disconnected lines. If not, and if there are also no overflow lines, the system will try to reset the grid to its initial states, because the initial states could be the most stable states, which can suffer a lot of unpredictable attacks. For the agent module, it contains two agents. The first one is a single-step topological action agent, which is a policy network taking the embedding of the grid states as input and the outputs a set of single-step actions to solve the current overflow situation. Then the system will use the simulator to sort these actions and will return the best action if the current overflow situation can be solved. However, during the experiments, we find that there are still a lot of overflow situations that cannot be solved with a single-step action. So we developed the following multi-step topological action combo agent. It can be regarded as a policy network equipped with a planning method to recommend a set of action combos. And these action combos are supposed to solve the current overflow situation in the following several time steps, rather than solving it immediately. Then the system will also sort these action combos with the simulator and return the best action combo if the current issues can be solved. Following, if the agent module cannot solve the current overflow situation, it means the grid will still overflow after processing the recommended topological action. Then in the emergency module, the system will first try to use the redispatch actions to elevate the overflow situation. Then the system will also give a judgment on the emergency degree of the current overflow situation. If the electric current is larger than a threshold, the system will try to use the predefined emergency actions to save the power net. And these emergency actions can be obtained by brute force searching the solutions of some corner cases of the overflow situation that our system cannot solve. And if the simulator finds out that the grid will break down at the next time step, the system will try to disconnect a line to make the power net live much more longer. For the alarm module, we developed a rule-based alarm mechanism. That is, if the agent module cannot solve the overflow situation, the system will directly raise an alarm if satisfying the alarm condition, which is quite straightforward and simple. We note that we also tried the network-based alarm module but it doesn't seem to work well because in most cases, the grid will break down in a few time steps. It means you need to raise the alarm as soon as possible if your system finds that the current overflow situation cannot be solved by your system, so that you can obtain much more alarm scores. The third part is about the match result. From the results, we can find that our developed system can achieve the best performance in both validation and testing datasets without spending too much computation time. The last part is about the future work. We find that there are still a lot of overflow cases that our system cannot solve. And these overflow cases are most caused by the disconnect of the line 49 and line 57. although our team did a lot of data analysis in work on these overflow cases, what we can do is just to brute force search the potential solutions that can probably solve these corner cases. So I think if there are any experts in this field, maybe we can work together to obtain much more better results in the future competitions. Okay, thanks for listening my presentation.
Okay, that's the winner from Polixer Technologies from China, Xiaojie Wang. So good to see 3 different ways of attacking the same problem, which is definitely what we wanted, diversity of responses. We will move on to the next presentation, which is going to be given by Fraunhofer, namely Walter Lehner. So if you're online, can you unmute, Walter?
Yes, I hope you can hear me.
Yeah, I can hear you. Yeah, 10
Perfect.
minutes.
10 minutes. I try to be on time. So I will say next quite a few times. There's some slides. All right. Welcome to the presentation. I'm going to present the project AI2Go. And the main motivation of our project was basically to look at previous challenge submissions and get a thorough understanding how do they work. Mainly the question also how much of this is actually deep reinforcement learning, how much is a brute force greedy approach. And we wanted to share our results basically to the community by providing a reworked baseline agent. And first of all, we had to say which challenge we want to look at specifically. So we decided on the robustness track for the one reason that there was the challenge ongoing for 2021, and also because there were quite a lot of submissions. However, we looked at other challenges as well, just to see if there was any other baseline that could be interesting. I would say next. So overall, to give you a very short timeline, we started the project at the end of September. Then we had a selection process in October where we looked at the different agents, looked at their code, how well did they work, was there enough documentation, do we understand how they work? Then we decided onto 2 candidates and then continued with the most promising one, went into understanding how did the candidate work, tried to replicate some of the training, and then basically where we are currently in January and February is that we are developing the baseline and simultaneously also a benchmark architecture to actually evaluate how well an agent works and also how well different agents work against each other. The end of the project is basically in April. So the idea is to publish both the benchmark, the baseline, and maybe even a possible paper depending on the results. And that's basically the timeline we set ourselves. Next. And coming straight to the selection process, so we looked at many different agents, and there were some difficulties depending on the version of the Grid2Op, on different availabilities regarding the code, whether or not they worked. Nevertheless, we found for the robustness track 2 very promising approaches. So the one was the PPO approach from Binbin Chen, and the other was the RL agent from the Perl framework. And then we basically looked a little bit closer into the 2 approaches. Mr. Martinez, I think, used the PPO approach as well in his approach. Next. So to give you a short overview, so basically the first one, the PPO approach, had a framework of a teacher, tutor, junior student, senior student model, where the first 2 were just a greedy agent looping through the actions and then actually generating data or training data. The junior student was then a neural network going into this training data and learning to analyze it and to replicate the tutor. And the senior student was then used based on the junior student to actually do actions within the environment. And in contrast, the RL agent was actually an evolutionary algorithm that was built on top of a greedy search prior to that. However, what we found most interesting is actually the action set. So the PPO approach basically had a lot of single actions, while the RL action actually had tuple or triple actions that basically had multiple time steps for doing actions. And we found that this might be one of the key reasons why the score was different between these agents. So it was not primarily algorithmic, but also depending on the action set. So yeah, as you can see, the score is 46 between 59. So there is quite a difference, but from our view and how we looked at it, is that it's a lot connected to the action set, basically. Next. So yeah, we decided to actually use the PPO approach for the main reason that this code was fully understandable from the training part until the submission part. And we could actually build an understanding how the agent worked. So for the RL agent, there were some parts missing and some in Chinese as well, which we were not able to speak. So we decided to use the PPO approach. And we then started to actually eliminate coding problems, execution problems, wrote some test scenarios, evaluated different sub-agents. There we actually found that the difference between the tutor and the senior student, so the greedy agent versus the reinforcement agent, wasn't that large, which was already quite surprising for us. Nevertheless, we had the major goal to reproduce the scores obtained in the challenge. If you would press one time, we can say, yes, we were able to achieve very similar scores to a certain level, but however, again, please press, there were some problems with the computational part. So to actually achieve the best scores, you had to run the PPO quite a lot, and there was some restrictions to actually get the similar scores. And as I said as well, please press, is that even though deep reinforcement learning was included, the greedy agent actually got most of the scores. So around let's say 90% of the score was actually done by the greedy agent, and only a small percentage was done by the PPO in the end. All right, next slide. Now, when regarding the baseline and the one we want to present in the end, we actually said we have to do some improvements, just simple code improvements. We know that in the challenge you do rapid prototyping, so we are doing currently some code cleanup. So Pylon, PEP8, looked at every function has type hints, write some tests, do continuous integration, and actually just enhance the documentation overall. But we also wanted to ensure some integration. So we want to integrate the PPO part into RLib. So we are writing some code there as well, include some hyperparameter tuning, and also cope with the grid to opt update. So we actually had to change some hard-coded parts in the code to make it more flexible. And third, we also wanted to offer some improvements. So on the one side, as I said, we want to include double and triple actions as well, but also in the training part. So from the teacher tutor start until the junior senior. And we also, if the time is still there, we want to enhance the net structure as well. So maybe even look at some graph neural networks. All right, the next slide. On the other side, as promised, we also want to deliver a benchmark architecture. So another part of our group is basically creating a benchmark architecture to look more into the scenarios and see how different agents are performing. So we already have Grid to Viz, but we want to enhance this a little bit more. So we have a reporting tool and a visualization tool that can actually tell us how well is the agent performing overall. Next. And we had some evaluation criteria. So we said we wanted to have some in the action-based part. So how frequent are the actions? How diverse are they? Especially on the robustness track, we have one primary part of one substation that is so heavily used Are there other substations which are not regarded? And also the sequence of length, as already told, are we only doing a single step, or are we using double or triplet actions? So this is quite interesting. Then we also want to look on the agent-based parts. So how long is the training time? How's the inference time, the cost of operation, robustness, and the performance overall. So this is also part we want to cover. And in the end, we also look at the context-based parts. So what substations are affected and how deep is the topological depth, and basically cover all this in the evaluation and return to the user who plugs in his agent, a script where he can actually understand what the agent is doing. So a lot of parts we are doing manually or did manually, we want to automate. All right, last slide. So basically, what are the contributions? First of all, oh no, sorry, yeah. First of all, we said we provide a learning baseline based on the winning approach. And we want this baseline to be easily reusable, fully tested, and also be applicable for other GridShop versions. We provide a new benchmark architecture for better understanding of your agent if you want to supply a new agent. And we also want to cover the amount deep reinforcement learning is actually enhancing the challenges. And this part is going to be very interesting, and we might publish this in the paper as well. Yeah, so that's basically it from our side.
Nice job, Malte. Thank you very much on time as well, so appreciate that. So yeah, it's interesting that you guys picked the PPO solution, and Horacio, who came at it with fresh eyes, picked the same one. So maybe the community might hone in on that as an option of choice. Maybe you can speak a bit more about that in the chat. But yeah, if you've got any questions, pop them in the chat. Hopefully you can hang on, Malte, and answer them in there, but appreciate the effort.
Sure.
Next up is a demonstration by NVIDIA, who have built a new simulator tool, visualization tool, that pairs nicely with L2RPN. So Pavel Dimitrov developed this video. I think he's online, so he should be able to answer questions in the chat if they come up as well.
We built a user interface to allow us to better understand what the learn to run a power network competition is all about. It interfaces directly with the grid op tools and allows manual control over taking actions at any point in time. We can also include agents or other logic that recommends actions at any point in time. So it becomes an effective debugging tool for developing the reinforcement learning agents as well.
Flip it.
At high level, the user interface is built as a Jupyter notebook. It is served by a Voila server, so it doesn't really look like a notebook, and one cannot modify it once it's running. We recommend using a modern browser like Chrome or Edge to run the application. They both work just fine. There are two main panels. One on the left that includes a representation of the grid and the current state in a map format. And the one on the right that includes all the control logic that we enable, as well as some tracking information and plotting facilities. In the control panel, we allow us a few important actions. We can load any environment that OptiGrid makes available. We can take actions like attempt a certain number of do-nothing steps, which happens to be a very useful thing to do a number of times. Most of the actions taken are do-nothing. The system will automatically stop if something bad happens, like, for example, the thermal limit is reached or is above 100%, or if a line is disconnected because an attack has just happened. We could also redispatch a generator. If we select one, we can redispatch a generator to produce more or less power. We have facilities to connect or disconnect power lines. And we can display a number of historical data by either here tracking it over time, given the actions that were taken over time, or displaying it directly in the map view. And perhaps most interestingly, we can also compute and recommend actions. The current implementation is an exhaustive search type of implementation, where for any given state, the system goes through all the possible actions or a subset of those actions and lists the top 3 actions ordered by the expected decrease or the expected thermal loading, the maximum thermal loading after the action is taken. Another feature of the user interface is the animation of power flow. We click on animate lines, and we get to see, relatively speaking, how power flows. And finally, the feature that is probably most useful for really large grids and mostly for the future has to do with the fact that the display of the grid itself is inside of an IPI leaflet widget, which is a map widget, and allows us to pan and zoom arbitrarily and better understand different parts of the grid. Perhaps the most useful application of this user interface is to try out different kinds of strategies. And we can try these strategies by hand. So in this example, we'll take the grid that was used last year and run through one of those scenarios. So first we load it, and as you can see, there are 36 substations and 59 power lines. And what we'll do here is to increase the number of steps that are to be attempted to 2,000 to make sure that at some point quickly we end up with a decision that needs to be made. Now remember, these are do-nothing steps, but they will be stopped if something important happens. So if we run it here, we see that after 139 steps, something happened. In this case, a power line was attacked. And there isn't a whole lot that we can do here, but and especially because nothing is really critical at this point. So we'll start and run it again. But before that, notice that we now have a disconnected line, number 56, and the 54 number here in brackets indicates how many time steps are going to be needed until we are now allowed to reconnect this line. So let's try it again. Well, now we ran for many more steps, and there are only 2 steps remaining until we can reconnect it. But we have a problem. We're now above 100%. So what we can attempt to do is to ask the recommendation system for an action that would potentially help us to fix this problem and go below the critical 100%. And as you can see, after having searched 3,000 out of the 13,000 actions that we're searching here, we've already found something that at least 3 different actions that should really, really help in this case. We'll let it run until it covers all 13,000 actions, and then we can choose one of these. If you go on the I button here, it'll actually tell you the details of what's happening. And now that it is done running through all of them, when we hover over each of the recommended actions, it'll actually also highlight what's happening on the map. In this case, it's all about the substation 16 and something happening on substation 16. So we'll just take this action, and sure enough, now the thermal loading is significantly better. Now, this line is still disconnected, but and also something new happened. You see substation 16 as one of the not substations that are listed. This is because you're not allowed to make action one step after another at the same substation. There is a certain period of time that needs to be waited until that can happen again. And so if we now run the possible actions, you'll see that in fact there are many fewer actions available. If we run all 100 of the 100% of the available actions, we see that there are only 1,300, just under 1,400 actions available out of a total that's closer to 67,000. And that's because most of these actions are actually something that involves substation 16, but substation 16 is not allowed as a place to take action. So we'll take one of these recommended actions again. Now you see it's on a different substation, and now everything is okay. Again, we're well below the 100% loading, and now this this power line is at 0, which means we can reconnect it. And if we click on this button, it will certainly be reconnected, and we're back in the green.
All right. So one of the more coolest tools I've seen in the last few years, developed totally from scratch by the guys in NVIDIA with no prior power system knowledge. So it's really an example of how L2RPN works, tying together kind of experts in multiple domains. Maybe Pavel, if you're on, you speak for 30 seconds on kind of what the plan for the tool is going forward, or where you think it's going, or even Ray.
Can you hear me okay?
Yeah, go ahead.
Yeah, thanks for inviting us. This has been a very useful and exciting kind of experience to learn about this whole new area for me, actually. We put together the tool to better understand what it means to run a transmission system, and to also allow us to get into arbitrary kind of detail manually about the various elements of the competition and the rules that need to be enforced. So we plan to release this tool to the community as an open source, in an open source way. We don't have a timeline. It should be pretty soon, so we'll look out for that. But the other thing that this allowed us to do, and this experience allowed us to do, is to also look at the simulation side of things a little bit more. And what we did was to implement the same simulator that was used here for the competition in the off-the-grid competition, the lights into grid simulator, and take a particular use case where you need to explore many different configurations and run them all at the same time. And I ported that to the GPU just to see what that would look like, and sure enough, you get a significant speed up that way. I heard several speakers mention that computational power is actually one of the challenges here. Simulating the grid, computing the power flows is one of the challenges. This was also our experience when we first started playing with this, and that's why the GPU accelerated version made a lot of sense. That is not as fully developed as what we're showing here, so that might take a little longer, but we would be very happy to work with anyone who's interested in this kind of accelerated simulation.
Thanks so much, Pavel. Yeah, any questions for Pavel, put them into the chat. We'll finish off. Yeah, we just wanted to spend a few minutes at the end talking about what the kind of next steps and also associated efforts that are happening, both short term and medium term. So Antoine, can you speak on the 2022 competition, Arena and WCCI?
Yep. So again, this year there's a new competition. It will build on previous competition, and this time will allow some battery storage to be used by the agent. So this is an effort led by NVIDIA this year. They are the main organizers, and we will help them to make that happen.
Great. Yeah, keep an eye out on the email and LinkedIn and social media channels for news on that. The Rosalie project at Fraunhofer, Frank Martin, 30 seconds if you can.
Okay, can you hear and see me, or most importantly, see me?
Yeah.
Hear me? I'm sorry. Okay, perfect. Thank you very much. So Rosalie is a small project that we initiated at Fraunhofer to well, support the further development of Grid2Op. And the idea what we have is there exists a GUI, graphical user interface to Grid2Op, to operate this agent simulation and go forward and backward in time, but it needs to load and reload and recalculate the agent all the time. So what we want to do is see if you can save or make some kind of a proposal or method to save the state of the agent, the eternal state, so that if someone wants to repeat the time step in the simulation, they don't have to run the entire simulation again until that time step, but rather they can load the agent from what it's basically doing and repeat the simulation again. So it's basically, it's thought to speed up the reversal of Grid2Op simulations a bit. So the idea will be, when it's worked out, released also to open source, maybe as a proposal to develop agents in Grid2Op in general. And if we do any coding, we can also find a way to make it available. I hope that was quick enough.
It was. Thanks. Apologies for rushing you, and your email address is there. It'll be on the slides when I send out the pack as well. So
yes, exactly. So if there's further questions, you can contact me there.
Perfect. There's a upcoming SIGRE working group. Anton is the convener. Do you want to speak a little bit on that, Anton?
Yeah, so AI is not like a dream anymore. It's being applied at industrial scale in several domains, and it will happen in the power grids. That's also why L2RPN is trying to explore what's possible, but then we also have to consider the risk. What would be the impact from an operational perspective of AI, and that's what this working group is about. You're welcome to join. We want a team from all countries over the world. That's what SIGRE is about. So if you're interested by the topic, try to contact your national committee member and to get nominated in this working group. It will be starting in March, so yeah, do it quickly if you want.
Yep, you can't add people to it. It has to be a nomination process, so you have to talk to your rep. It's important to note. But yeah, so get in touch with those. The Global Partnership for AI. So this is an initiative kind of being led by Priya Donti and Lynn Chak from the Center for AI and Climate. So they've released a report in line with the COP21 conference at the end of last year, which were recommendations for government action associated with enabling AI to help with climate change. So L2RPN featured as a use case pretty prominently in the report. It's a really good report. It really aligns with everything that we think about what the future would look like and what could help. So there's a link to the report in the slides, and also the really good interactive community forum, community.climatechange.ai.home. So there's a lot of people on there contributing, lots of good channels. So feel free to check that out. This is from TU Delft, so they're launching a free open online course, a MOOC, and it's starting in 8th of February, which is next week, I guess, early next week. So feel free to Google that or check it out. It's free to register on. It's 6 weeks, 5 to 6 hours a week. Our colleague Joshin Kramer is involved in setting this up and thinking about it, so we're definitely in support of it as much as possible. And this one is back to Anton, the Learning Industrial Physical Simulation benchmark.
So yeah, it goes back to the full ecosystem of L2RPN. So we're also interested into using simulators and accelerated simulations. That's also what Pavel mentioned. And so we're developing these benchmarks for AI augmented physical simulators with machine learning, which uses also Grid2Op. And this is done through the HSA project that is led by IRT Systemix in France. So this will be released around summer 2022 and available on Codabench. And this this will be submitted at NeurIPS this year.
Thanks, Anton. Hardek Kyo, very quickly, we're just at the hour, or at the half hour.
Yeah, thank you very much. So this is funded by US EPRI government and agency. So we are partnering with Vienna, Google, and Pacifica, trying to another kind of a control applications for dynamic control instead of a steady state control, and targeting for post-event emergence control. And what we did is to scale up these problems to a larger scale. So we definitely relied on high performance computing, and also we leverage high performance grid simulators. And so far we have been working in this project for 2.5 years, and we have been testing our methods both in a 2000 bus synthetic text system as well as recently in a WEC system. So we have more results sort of in these two websites. So if you are interested, and I can talk more with you offline. Thank you.
Yeah, website links are there. They'll be in the slide pack, so check them out. It's a really, really interesting, cool project in the States. Lastly, we in EPRI are trying to put together, get together some SMEs in data science, AI, ML in European TSOs, trying to develop a kind of common framework or simulation methodology for control center or transmission operations tools. So including kind of things like data standards, governance, ethics, simulation platforms, use case development, visualization. So we're working with a few TSOs already, trying to build a collaborative. We're going to engage with the European Commission for supports and funding, engage with the US government also for supports and funding, and hope to develop projects late this year, early next year. So if you're interested, just email me, akelly@epri.com. And there's other couple of things like AI for RealNet, Grid Pack Wind from PNNL, and the 5 grand challenges from EPRI. So they're all available here and are available in the slide pack as well. We just don't have time to cover them, unfortunately. To get engaged, we have a Discord channel that Benjamin and Antoine are manfully manning every day, so responding instantly to any questions about it. So get on there, search it on Discord. We have an email circulation list. If you want to get add your name to poll question 1. We'll leave it open for a few more minutes, and we've got websites on epri.com and also a YouTube channel where we'll post these videos in the next few days. And there's some papers and references there also in the slide pack, which have been developed in the last couple of years too. That's pretty much it. Apologies, we ran a little bit too long, but if you've got any questions, we'll close the audio, close the video, but we can stay on here on the chat. If there's any more questions, feel free to ask them. I'd like to thank all the speakers, especially all the guests that put the work into their videos. Thanks to everybody for joining and contributing and asking questions and responding to the polls, and hope to see you all soon. Thanks.